All right, so I must say that when Per invited me for his 60th birthday, I didn't know that I had to present a talk. And so all of a sudden, one day I received a message from Yanis saying, you know, please send me your slides. That's where I panicked. But this is actually a quote from a very famous American philosopher. You know him, right? No?
So I'm trying to remember. I remember the quote, but
Okay, so it's from a guy called Yogi Berra.
yeah.
I could tell you a lot of these things. I like that guy. So I panicked for a while, and but then I remembered that in 2004 I gave a keynote address at IPDPS that was about this topic, and so that's what I was saying, is that you can always look at the past to see if the predictions were correct. And you can, that's what people do, right? They use data from the past to predict the future, but that prediction is not reliable. So I'm going to try to keep it simple. It's not technical. And so you're maybe not going to learn much, except that I make a point, right? And of course, that point is a prediction, right? So it's about the future. All right, so how do I move this? So actually, a lot of the slides that I have here, they come directly from that the keynote in 2004 at IPDPS. And the reason I pulled them off is, of course, I didn't have the time to do otherwise, but is because I think they're still relevant. And actually, these slides are directly taken from that talk, except that I've reduced drastically because I didn't have the time to cover all these slides. That took an hour and a half. So what happened is that there was a lot of research in the 1980s and 1990s about parallel architecture and all kinds of form of architecture, SIMD, MIMD. By MIMD, I mean using multiple processors to execute the same program using multiple threads. Systolic data flow, shared memory, etc., etc. So, and then came the era of the Intel micro, and it looks like today those ideas are back in vogue, according to Yale. So, what I'm going to do is that I'm going to look at the history of some predictions. Some are good, some are bad, and some are in between. Okay? And then I'll talk about the future of computing, which is more prediction, and then I'll talk a bit about PER. So first of all, exponentials are bad predictors. They are good while they last, and at some points they break down. So these are slides from 2004, right? We're trying to, and this talks about the miniaturization that we are in CMOS. And you can see that those predictions at that time, they were okay, but they're still too optimistic, right? Because 2009, we would have a gate length of 15 nanometer, and we are in 2018. This one is about frequency. We all know about that one. That one stopped at 2003, and on the semi-log scale, it looks like this frequency is going to go up forever. And 2003 is about the time when it started to stop. So I gave that talk right at the time when things were changing. And then the one that I love the most, because I worked a lot on that thing, is the memory gap. That memory gap apparently was going to grow forever, and we didn't know what to do, and that was going to call, we're going to meet a wall, blah, blah, blah. And then what happened is that that wall was never reached because it flattened out. So today we have a lot of technique to take care of that. I would like to talk about other people's prediction and then my prediction. There is an issue of IEEE computer, September 1991, that has got a lot of prediction in it. In that issue, I just focus on the architecture one. In that issue, Harold Stone, which is a famous architect, and John Koch, even more famous, they published a paper called Computer Architecture in the 1990s. I don't know if you have seen that paper, but you can find it online on IEEE Explorer. So they made an argument in that paper explaining why 250 megahertz clock would be difficult to attain, and that 1 gigahertz would be the maximum. And that's because of interconnection. So the conclusion of that paper is that the 1990s could end with the entire line of computer offering affected by fundamental limit on clock speed. It's kind of not bad prediction, but it's not totally accurate because the things that they don't know in that paper is that people started to pipeline wires and also have multiple layers of wires with different speed. So they didn't know that. It's not in the paper. So that's why it's very hard to predict, even the best people, right? You don't know what people are going to invent. I have some of my predictions, and they were doozies, but also there are, if you look at prediction, there are proposals we write that don't pan out, and when they don't pan out, we have to use them for something else. That's a prediction. And then also projected industry, but that's also predictions. Then this is for Yale. Computer architecture is bet the farm on all speculative, doing speculation everywhere. There's a list of things there, but I could give you more. Of course, when they don't pan out, bad things happen. This is something that I want to go fast. Here, there's a bunch of numbers here. So that was in 2004. That is the semiconductor technology roadmap. And they predicted that in 2016, which is 2 years back, the chip frequency would be 29 gigahertz. Wow. All right. So, and people were writing paper using these numbers, right? So, okay. So, again, this is a prediction, right? And actually, that's what I said in that IPDPS keynote. And my view is that it's rather bleak. There's no new big idea there, and there are parallel systems, but they have problems. Amdahl's law, lack of parallelism in many important applications, and then the problem of parallel programming, much more difficult than sequential programming, and then the overheads of communication and synchronization. That topic has been beaten to death. But there is a question that I would like to ask, if somebody here can answer it, not now, but later, offline. There was a machine, the IBM RP3, that was built at the end of the 1980s. And at that time, the clock rate was like 10 megahertz, right? And so the ratio between communication, even if it was through cable, the ratio between communication and the speed of the processor, there was a factor 4 between the speed of the processor and the communication time. Now, today people are telling me that the world has changed, but at that time in the RP3 it was already impossible to program efficiently multi-thread programs because of the communication. So I don't know what has changed, because what counts is the relative ratio between the speed of the processor and the speed of the communication. But so I'm going to skip that one here. So I would like just to cover the last thing here. We were talking about Hennessy and Patterson. They just received the Turing Award. And both agree that there is nothing more to find in architecture. If you read that article in ACM News, they both agree that there's nothing else to find in architecture. So, already in that keynote, I was looking at to build the giant warehouse called data centers, connected to thin clients. Again, there's nothing new here. It's just wireless plus multiprocessors. But it makes a lot of sense in terms of power, energy, and programming complexity. So, but there are some problems still with that. So let's say that this is the future. It's not clear that users will want to give up their privacy and their own device. And execute things remotely. There are security problems, and Yale presented that. So there are software and hardware. The hardware problem comes from the fact that we are mixing different threads, and so thread can learn about other threads. There's the problem of reliability, and of course, as we are running below the threshold and we are shrinking the dimension, is going to get worse. So security and reliability may be important problem in future hardware. Okay, so this is the very sad conclusion. When we reach the CMOS endpoint, which is, I don't know exactly how many years. I don't want to predict that one. We'll be left with some kind of parallelism, whether it is homogeneous, heterogeneous, or accelerators and general purpose, and it's not clear that we are going to be able to maintain the exponential growth in compute power like the one we had, and so in all likelihood, and this is a prediction, it is a very sad one, when we reach this dead end, the golden age of computing will end too. But this is a prediction. So who knows, right? That was already in that keynote. It's kind of a sad keynote, but Now about PER. First of all, I would like to say a word about how I met PER. Okay, so what happened is that all of a sudden I received a letter from Lund University by Lars Philipson, who was the advisor of PER, inviting me to his. I was going to be his opponent at his thesis, PhD thesis presentation. Right? So that was a fun time. There were 2 days. There was good food. There was a lot of drinking, and it was also. I have been told no drinking joke. Okay, especially the extreme drinking joke. No one, because otherwise they're going to cut it. They're going to edit it out. That's what they say. So it was a great thing. And then actually after that, that's how I met also Karina. And after that, we became friends, right? I went on sabbatical for 6 months in Sweden. There was a fun experience too. It was dark most of the time. It was in November. And he attended my weddings with an S, and then I attended his wedding. And so we became very good friends, and also we had a very productive cooperation due to this friendship. That's what I wanted to say.
Are there any questions? Yes.
Okay, Joseph.
So, Michel, why is it that those who say there's nothing else to do, everything is invented, usually are advanced in years, while young people don't say these things? Why do you think this is?
Okay, well, that's because, of course, we are getting old, and I mean, I was going to, I forgot to, I forgot to say that because I wanted to say something about Yelpat again. The thing is that in the past, there were big problems, okay? Yes, there were big problems. Okay, well, you disagree. But the thing is that there were big problems. Like even the RP3, understanding parallelism, understanding how to program. There was also the Stanford project, and when I remember that when I was working on sequential consistency and other consistency model, I felt like there was an exciting time, right? I thought that I was working on some basic problems, and I felt like I was sailing. I had the wind in my back, right? It's not quite the same now. Is it because we are getting old, or is it because you say it's because I'm getting old? But I think that, and it maybe NSE and Patterson are getting old too. But can I finish because you are attacking me here? So the fact that there is, I remember, for example, the memory models and coherence. I got my tenure out of that. I worked I worked for 5-6 years on that thing. Some of it with PER later. But I don't think that there are problems like that today.
So you think, for example, that getting all the Internet of Things and all the devices together and getting them to work in the whole world is not a problem of the same caliber?
Yeah, well,
There are bigger problems than the Internet of Things.
I was talking about architecture here, okay? I'm talking about architecture. I'm limited to architecture.
I have the mic in my hand. Do I need the mic? I don't know. I think so. First of all, age has nothing to do with it. There are plenty of computer architecture problems. There are many things that we'd like to be able to do that we don't have computers fast enough to do. You showed some of the things. Manolis talked about. People say that there's no need to get the I/O faster. Of course, there's a need to get the I/O faster. And once the I/O is faster, the software will catch up. But nobody's going to write software for a machine that doesn't exist yet. We heard about the meltdown and the Spectre and all this. Are you willing, in order to get security, to have your computer run like a dog? I think it's foolish.
There's the problem.
So I think it's foolish for anyone to say there's nothing left to do. That shows incredible naivete.
I didn't say that.
You didn't say that, but you referenced a paper, apparently, that Hennessy and Patterson have now said it's all been done. I've heard that.
Yes.
I've heard that many times. I've been doing this for over 50 years,
yes.
And I keep hearing it's all been done, and then something comes along. Gee whiz, it's not all been done. Okay, I'm ranting. My mother here tells me I'm ranting too much.
I think that I don't like this sentence, okay? And this is the saying that David Patterson say in China when he got the Get Mowgli. You get the Get Mowgli and you say to the all young people, you are in a very bad topics, don't do anything, okay? So my interpretation is that John Hennessy and David Patterson stopped doing research when the multicore, okay? And probably they don't know really what the people...
I was just quoting them, that's all.
No, it's nothing against you. It's nothing against you. It's just commenting this quote again. So probably they stopped doing research, sure. When the multicore arrived, the first multicore was just putting single core together. But after that, there are a lot of research in the communication between the runtime and the architecture. And then, as I will say in my presentation, the future. I am very positive about the future. I would like to have 25 years and to devote my time to computer architecture, no doubt. And even worse, if they got the Alan Turing because they work on computer architecture. They shouldn't say that. I will tell them.
All right. So it's heating up. That's good.
I've seen I've had enough.
Okay, let's stop it here. Michel, this is for you. Thank you very much.